So today we'll discuss about generative AI for building dialog systems. And by generative AI, we are using the term slightly differently, that we are mainly pointing towards these new technologies that have come up related to LLMs and SLMs. Okay, and the slides are fairly short, and also like I have two small demos. And so if you have any question, just interrupt me and ask me in between. Right. So dialog systems has like one of the longest histories in terms of different applications that this ML research area has focused on. So it started back in 1960s with bots like Eliza and Perry, and there it started with systems which just included a set of rules like if A then B. Right. So from there we have made like significant jumps throughout the generations of models. Like from rule-based systems, we had moved to planning-based systems, increasing the scope of what sort of context it can capture. And then from there, we have moved towards RL-based systems in order to learn policies automatically, so that we don't have to hard code or like manually write these rules. And then from there, we have moved towards deep learning-based systems. But although we have gone through so many generations of dialogue generation models, so it has been one of the most difficult tasks for deep learning as well. So earlier rule-based systems used to face the problem that your scope of these models should be very limited. With deep learning, that was resolved, but many problems still existed. For Many problems still existed. For example, the initial models based on LSTMs, GRUs, sequence to sequences, they used to face the problem of mode collapse, or where the model would just focus on generating one particular response, no matter what the context was. And also, these models tend to perform very badly when the sequence lengths were long enough, like even longer than 2 or 3 sentences. So from there, from the first generation, we moved towards more complex methods like variational autoencoders or VAs and generative adversarial networks or GANs. With that, we tried to solve the problem of diversity, that these previous generation of models were mostly focusing on generating only the most frequent responses. So VAs and GANs were able to help a little bit in terms of diversity, but still the responses remained meaningless. Like irrespective of the context, it would generate something which had no semantic relevance to the input. So then came the time of transformers. So transformers, although they were similar in terms of how they work, or like what sort of models they are in terms of like they do sequence to sequence encoding or just an encoder or decoder only model, similar to what LSTMs or GRUs did. Transformers allowed us to have very high capacity in our models, and the parallelized training also allowed us to like train larger models. Right. So although the initial transformer-based model still had problems, but those problems are later resolved. And the final problem that remained was lack of reliable evaluation metrics. And this is still one of the biggest problems in developing dialogue generation systems. So although we have come to a point where we have reliable ways to build chatbots using LLMs, but doing faithful evaluations to what we humans expect from these systems. So evaluating for those quantities are still difficult. So all of these are still like open research questions, but we have some hopes now with the advent of LLMs. Right. So like dialog system faced all of these problems almost over like more than 80 years, but now we have finally some success of something that we can call real like usable dialog systems, and may as well pass our old definition of Turing tests, right? So what brought about this success? So the main factors were these models had like lots of parameters. So from few millions of parameters in previous generation models, we went to hundreds of millions. From their billion to now we have hundreds of billions or even trillion scale models available that we can access on a day-to-day basis. Right. So this is a significant increase in capacity. And also because of this availability of better GPUs and everything, we're able to train models on corpuses that spans trillions of tokens. So overall, it seems like the main problem that previous generation of models are facing in terms of training deep learning based dialogue systems was the capacity of these models. So we needed to train the models on much larger scale and for much longer to be able to understand language in a human like way. Right. So what are the problems that we need to solve in like in 2024 or going ahead? Right. So there are many problems related to the different kinds of applications that we're trying to build in like in industry or for personal usage. So obviously the first problem that we face is response generation. So this is like the core of this field, like how to generate a valid response given any context. Now, this can be the situations in which this response generation task comes in can be very complex, like can be varied also. For example, there can be domain specific scenarios where you need to have certain domain knowledge, you need to conform to certain ways of giving responses. So there can be some rules which are specific to the domain, and you have to kind of stick to those rules. Whereas you can also have a setting which are generally open domain. So in these types of systems, our main intent is to generate responses for any kind of queries, right? So it should have a high amount of knowledge. So the models need to capture like a large amount of world knowledge, and should be able to please humans very well, like engage humans in conversation very well. So in domain specific chatbots, we don't usually look for how fluent the English is or anything. We are just looking for the correct answer. But in open domain, we want the bot to be able to engage the user for a long time, right? And aside from the response generation task, we are often interested in smaller like subtasks also that comes as part of dialogue understanding. So it can be like action or intent prediction. These might be useful in systems for say building like Google Assistant or Apple Siri, right? So there you can have system like usefulness of this when you're trying to set your alarm or trying to open an app. Then there is the also requirement of dialogue summarization, that for like news purposes or other purposes, you might want to summarize a long debates or something, like to a small summary. So this requires understanding of the dialogue structure, which is often different from a normal generic text. Right? Then the challenge of evaluation that I earlier explained, that evaluation is still difficult. And with availability of LLMs and their general language understanding capabilities, we actually can use these LLMs itself for doing evaluation of dialogue generation models. Right. So beyond all of this, there are also challenges related to controllability of these LLMs. So often so when you build a chatbot using these LLMs or any sort of system using these LLMs, you want to know how these models perform. Like you want to know, given a particular context, given a particular scenario, what the output of the model is. Like you want some ideas. You don't want it to be giving away secret information or be biased to certain minority groups. So all of these should be taken care of. And for that, the current approaches are guidelines and safeguards, but they are not foolproof. So this is also open question that like lots of research is going towards these problems. Then there is the challenge of how to provide and maintain world knowledge. So the world is changing every day. So you have new information coming in for this, new information coming in every day, like the prime minister changes or the results of election changes. Result of election is like a new information after certain time point. But this GPT-4, for example, is bound to a certain point in the past, right? So it has seen data till say 2023. So how do we keep updating these models? Because retraining these models would be very costly, and also it's not easy to just do a little bit of training and expect the models to be performing, like continue to perform equally well what was there before this training phase, right? And then there is the final problem of cost related to LLMs. So LLMs are very large decoder only models, at least of the current generation. And there, when you try to do inference using these models, a longer sequence length means a quadratic cost or quadratic time and dollar cost on that. Right? So minimizing costs through either say going towards smaller LLMs, improving smaller LLMs, or even compressing your inputs or output sizes is beneficial. Right? So all of these problems exist. So we'll like start from the response generation part and try to see like what are the different approaches there. And so just to before we move towards this specific problem, so the standard approaches that the research is looking at right now are mostly related to fine tuning SLMs, LLMs or SLMs, and also how to make these SLMs better. So this is one approach that whatever task you at hand, you can fine tune these models towards those tasks. So how to do those efficiently? So we have parameter efficient fine tuning methods like LoRa coming from those kind of research. Then you have approaches like prompt optimization. So most of these approaches for building systems using LLMs often require certain prompts, right? And these prompts can get very long, and you can only get to the right prompt through a long phase of manual trial and errors. So how do we quickly get to these prompts is also a question. How to find the best prompt for these systems is a challenging question. So there, like various work is trying to do find out optimization method for this prompt. And since this is discrete space, standard deep learning methods don't work here. Then there is then there is the problem of input and output representations. So you can represent input for various tasks in different ways. And since the general mode of input for LLMs is text, and nowadays like in image and audio are also coming up with GPT-4 4o. So there we need to convert the task input to any of these representations, right? So for example, if we had a math question that can be written in say just like mathematical form, you might need to convert that to a textual form and explain it properly so that the LLM can solve it. So input representation is also a challenging task. How should you convert your task inputs for that purpose? And then there is the also challenge of output representation also. For example, if you are in a domain specific scenario like code generation, you want your output to constrain to certain formats, like it should be a compilable code source code, right? But in LLMs inherently do not have this capability to sticking to certain formulations or certain format for outputs. So this is also open challenge, that how do we make sure when you're trying to output the structured data that LLMs do well and do not deviate from those formats. Right. So if you have any questions at this point, I guess you can ask before you go ahead. Okay. Great. So if there are no question, I guess we can continue ahead. Right. So I'll just go over a few examples of how we like what are the steps towards building dialogue systems using LLMs, and what are the general approaches and findings that we have until now, and what are the general norms followed in industry and academia. Right. So the code, like the example code that I've built here, is mainly focusing on the llama model. And so like all of these models can be very difficult to load. So the code base that I have is using the llama 2 model, and that might even require more than 50 GB of GPUs. So oftentimes you might want to modify based on what resources you have access to. You might want to modify it to change the data type, or like use a smaller model instead of 7 billion, go towards some 3 billion model, or find even something smaller, right? So now all of this comes at a cost. When you are trying to work with a smaller model, the accuracy or quality of the responses might suffer. So all of these are current research problems. So, and the best prompting techniques and everything that we see are usually coming from the GPT-3 and GPT-4 side. And these smaller models only share certain properties of those, like a subset of properties of those, right? So yeah, so we should just keep that in mind. So whenever you are building something, you have built something, make sure you ensure that works for other models before going towards or deploying with a different model size, right? So things change in this domain. Okay. So the like library that I'm showing here is based on the VLLM package. So, so the most common API that is used for all of these inference tasks is the OpenAI API. So that started with GPT-3. And since then, there are like lots of models have come up in this SLM area, like Llama 5, Mistral, Gemma, all of these things. And so that our code like you can work with one code base and change the models easily. So that's why this VLLM package was built. So the OpenAI package only works for the GPT-3 onwards models and only from the GPT family. So if you have models like Llama, etc., so that those are coming up on Hugging Face. So that process of like instantiating that model on your system and installing that, downloading that can be difficult. And also you have to write a custom code. So now if your task is just related to say inference and you want to do prompt tuning to uh, build a chatbot using that, so you can just utilize this VLLM package, which gives a very easy API point for inferencing. It does not allow training or anything directly, but for inferencing, this is like a perfect companion. Right? So the installation is fairly easy. You just do pip install VLLM with like you can create a conda environment and then do a pip install VLLM, and after that you just call this command. So there are a few more arguments here, but the most important ones are the model argument and the dtype argument. So the model argument will let you choose any model from the Hugging Face repository. So for example, here I have picked Llama to 7 billion, and you can pick any of the checkpoints that exist. Of course, like older generation models like GPT-2 might not work here. So those are like before all of these OpenAI API came up. So post Llama models or post GPT models, most of the things should work, most of the generative models. So it includes Llama, Mistral, Gemma, all of these works out of the box. Right? And I'm mentioning here the D-type option here. So this is using bfloat 16. So usually these models are trained in 32-bit data, like 32-bit data type precision data type, but that can like require significant amount of RAM. So just by using bfloat 16, you kind of have the GPU RAM requirement. So you can go further beyond this as well. So there are 8-bit and 4-bit integer modes available also, but all of this comes at a small cost of the accuracy or the quality of the inference that you are doing, right? And the other way of decreasing this GPU requirement is you choose some other model. So for example, this is 7 billion. You can go beyond this also. So there are like 70 up to 70 billion models available publicly. And if you go towards the lower side, you have 3 billion and 1 billion models available. Okay. So I guess we can go to the code base now.
I have a question.
Yeah, go ahead.
Earlier, you explained based on the parameter size, the model performance would change. We can choose 4, 8, or 16. Um, so, is there a change in performance uh, uh, same is proportionate to the change in the size of the parameter, or it will drastically decrease if we take 4 or 8?
Right. So the performance drop is not drastic usually. So at least for the D type. So this method is actually quite robust. So decreasing or like changing it to a different floating point mode. So from 32-bit, you can go to say 8-bit integer mode. So there the performance drop is usually not that drastic. The model remains fairly similar. There is like maybe up to 5% or 8% drop in performance, like relative performance. So 5% relative performance drop.
Okay, thank you.
Yeah. Although on the other side, so if you are going from say 7 billion to a 3 billion model, so there the performance drop is much more drastic than changing the data type. So it is always recommended to find out a setting for, suppose you have found that okay 7 billion model works very well, and you would like to continue to use that. So don't change on which checkpoint you are using. Try to use the best checkpoint and see what is the optimal setting you can have with respect to data type and other things. Okay, so D-type is like the best way to decrease the model RAM usage size, RAM usage.
Okay.
Yeah, right. So so now towards building this chatbot. So what can we do? So first of all, we need a prompt. So all of these LLMs are working based on prompt. So the raw LLM checkpoint were usually fine-tuned on a large corpus of generic text, right? So if you use those models, the prompting task is a bit hard. So there are models that have been trained for this purpose particularly. For example, if you see here, the checkpoint I'm calling has this tag HF at the end. So this means human feedback. And there are multiple variants of all of these models. So for example, there is a Llama 2 7B, then there is Llama 2 7B HF, and there is Llama 2 7B HF chat, right? So there are these different variants of model. And not all of these models will work equally well with prompting, and the same prompt may not work with them. So for example, if you take the raw Llama checkpoint, so that is usually useful for fine tuning it downstream for other tasks, which is not, maybe is not captured by prompting, or you want to create a new small language model using your method. So then you have to go from the usually you would like to go from the raw LLM. But if you want to build model like systems for like chatbots and stuff, it is recommended that you either use the instruct gpt, or the human feedback RLHF based models, or the chat models, right? So the chat models are even better if you are just trying to get a chatbot. And if you want to do some tweaking, like you are not trying to build a direct chatbot using just prompting, but you want to add some, say, some knowledge there, or you have some domain specific instruction that you want to include. So all of these can be helpful. All of these can be better tackled by the just human feedback RLHF, right? So now to build the minimal system to for this to minimal system for a dialog system, what you have to do, you need to have some structure in the data, right? So if you just give a running text, it will not be able to understand that you are trying to do like you are trying to mimic a chatbot. So what you can see here, I have added these two tags like bot and user. So if you see on any forums or any blogs, usually people like in the past people used to show examples of dialogues or conversation in this format. So this is like a very common format that is there in the original dataset. So this template usually works well. And this is like commonly is always there in most chatbots that exist there. So we can add stuff around this, like before this and after this, to make tune our system more towards our application. But this basic structure usually exists, and this with this minimal structure you can have a like simple chatbot, right? So let's go to the code now and see how to like go from the starting. Okay, so the first step that I mentioned is installation. So you need to first do this installation, like pip install VLLM, and then after that you need to start this server. Okay, so this will give you a OpenAI compatible server for this particular model. Now, once you have done this, so this will be done from the terminal. So you have to start this server in the terminal, and then you can go to a Jupyter notebook or a code for doing your actual like implementation of the application, right? So once you have started the server, so my screen is still visible, right? And you can see the code. Am I showing? Okay.
Yeah, I think the answer is yes.
Okay. Okay. Great. So right. So first, you would like to check that before you like start coding, and if you are inside a Python environment, you can get like cryptic errors which will be hard to debug. So just to ensure that the API that you have started is running properly, because there can be some errors, like the model may not have started like the model may not have started downloading, or it may not have finished downloading. All of these problems can happen, or maybe you did not have access to this Llama checkpoint. So Hugging Face requires you to sign a terms and conditions page to access this model. So if you do not have accepted that or logged into Hugging Face, you will see some error while starting this model, right? And if you have like started this model on your terminal and you directly go into coding, it might be hard to debug. So it's always best to try like just a simple like REST API call to see whether this server is running. Like, so this is just calling this URL and trying to see whether it is able to get a simple completion. And if there is any error here and you are not able to get a response like this, then you should understand that the problem is on the server side, that your VLLM server is not working for some reason. And if that is successfully running, then you will get a JSON like this. So it will have fields like ID, object, the choices. So these choices are the actual completions. And so as you can see, like this was the request. So the system prompt is like you were a helpful assistant, and then this was the role. and it gives some response. So the response is not that good here, but basically it works. Okay. And so you can also make another request instead of the first one. So this will give you the list of available models. So with VLLM, you can deploy multiple models on your server. So here in this case, we have just only one model running, so which is the Meta Llama 2 model. But you can have multiple models served, and that you can check from here. Okay. Right. So once you have this server running, so this is the actual Python logic. So this is where the Python logic starts. So all of this will work with the OpenAI API directly. So you don't need to install any more libraries to work with VLLM. And if you have an existing code base for GPT 3.5 experiments, you can just use that directly here. Right. But although some prompts may not work that well, so you'll have to play around with the prompts and everything. Okay, and the first configuration parameters are the API base and the API key. So you don't need to mention the API base usually for OpenAI, but since now we are hosting this model locally, you will have to give the API base, so which is localhost port 8000. And we did not set any API key in VLLM, so this is just anything, any random string. It will not matter. And if you have so there is a flag to set a API key for the VLLM server also if you want to keep your uh, like running server separate from any other folks accessing. So then you can have API key also. Then you have to mention that. And yeah, so the next step is to start this client, which is just building OpenAI object. And once you have done that, you can start doing basic prompting, right? So the first thing, like the most natural thing with any GPT or like any LLM is the completion, right? So you give it any prompt, like San Francisco is any textual prompt. It does not have to conform to any style or anything. So you get a completion response. Like San Francisco is a city of many neighborhoods and so on. Right. So there are few parameters like temperature, max tokens, few I have not shown here like top P and other frequency, all of other things. And also there is a possibility of detection of special end of sequence tags, like, and I'll show like some usage of those, like why those can be useful. So here, when you are using this like Llama 2 model with this from San Francisco is it? So you can see that the model started with a okayish response. So this was, I think, valid. But beyond this, it started repeating the same sentence, right? So there are two things that are happening here. So one, I have set the temperature to 0. So this helped me have a sentence which is more or less accurate. But this went into the problem of repetitions, right? So these models have certain like mode collapse problems. So when you have a sequence that you're trying to generate, somehow the same sequence repeated always have a very high probability with these models, right? So if you just put temperature equals 0 and start to decode, it will generate something, and then at some point it will start repeating the same thing. Okay, so this is a common problem with this model. So what the solution is that you use a non-zero temperature, so something like 0.8 or 0.9. So when you increase the temperature like to 0.8, what happens that the model starts to sample. Now, when you allow this, you go away from like greedy decoding. So the greedy decoding was doing the highest probability sampling, but now you have gone towards some other low probability tokens that you would be sampling. So this will increase the diversity. So as you can see, like the model is at least not repeating anymore. So it is giving like new sentences. It still has a repetitive nature, so it does not stop properly. Like it could have just said San Francisco is a state in US and just be done with that. But we continue to generate some random things, and many of the things here still might be incorrect. So with higher temperature, that is the problem. You get diversity, you get better quality of this generation, but the correctness of these models can go down. And also, since we are using the Llama 2 model here, so this is just 7 billion model. So a common problem with these smaller scale models is that they lack world knowledge a lot, right? So if you are using GPT-4, you can get very like totally correct answers most of the time. So whatever question you ask, 90% of the time you can like reliably say that okay, my answer is correct. But as soon as you start coming from there, like GPT-4 is like almost trillion scale. So from there you go to billion scale models, and now we are hundreds of billions to now we're like few billions of models. So the damage in terms of how much world knowledge is there in these models is significant. Okay, so you will have to take care of this aspect also. So if you're using smaller models, you have to think about whether you want to use some sort of like retrieval augmented generation mechanism or something. So these things you need to keep in mind. Okay, so all the examples that I'm showing will be Llama 2, and you will probably see some inaccuracies in the responses. Although they will be like fluent English and everything, it will be something imaginary which might not be which might not be factual, and these problems will be there. Okay, so now, so this is still the completions API that we are using. So what the completions API does is that gives you access to like the raw API in the raw mode. So the API function does not make any changes to the prompt that you are giving. So for example, if I am writing this user colon this first question about battle of Plassey, and then I put this prompt like this prompting token AI colon. So this will just send this sequence as it is to the model, and the model will start generating from here. Whereas if you are using some other like ways to call, so for example client.chat, so then it can be different. Okay, so in all of this till now I have been using client.completion. So this completion API is giving you access in the like raw mode. So as you can see, this is only what went to the model, and beyond that, it just started predicting this. Now, as you can see, the same we are facing the same problem again without any structure or anything. If you just use the raw LLM as it is, it will not give you the desired behavior. It will just like end the same. It will not end it after this utterance, and it will continue predicting. So that's why usually we want certain structures to be there, and the OpenAI API has some of these structures inbuilt. So one of these ways to do this is the client.chat mode. So this will add some tagging. Okay, so right. So just one thing here. So how do you build a bot using this? So for example, the first prompt was this, the user query, and you want the AI to respond, the bot to respond. So you just do AI colon. And one thing to notice here, so this is how this Llama 2 HF model was trained. So the HF means human feedback, right? So the RLHF was done in a way that it should not give anything wrong. It should not generate anything wrong. But see that how brittle this mechanism is. So in the first response, it actually correctly does that. So although we do not want this from our model, like we want our model to respond to our question, but since the model was like during the RLHF period, it was trained in a way that it should not give any fake information. It stopped from doing. So that was what was expected from the developer side, let's say. But as you can see, when the model went to the user mode, so it started predicting the user utterance by itself. It did not stop from predicting like some fact, right? So this fact could have been wrong. So here I think it is correct, which is good. But in certain cases, this could have been wrong. So as you can see, like we need bells and whistles to like safeguard these systems. If you just use it blindly, we'll face problem like this. It will not follow the guidelines. So it first initially followed, and then it forgot about the guidelines, and all of these problems can happen, and it can continue to generate new utterances without stopping. So we need some boundaries that it's going to. We need to set some boundaries, right? And yeah. So moving on. So that was like the raw, like just by basic prompting, how you can build a dialogue system. You just give some basic structure that you say user one colon, user two colon, and that you allow you to change users, and the model will understand, okay, there is some conversation going on, so I should probably generate the next response. Now, as you saw, that can have some problems. So what do you do? So the OpenAI API has a chat mode. The OpenAI API has some a chat mode to handle this. So what chat mode does is it adds certain tags around this around the prompt that you are giving. And also notice that the way you were giving prompt changed. So earlier you were giving a raw text as prompt, right? So the prompt was just this string, and that's what it was going into the model. But now we have changed this to a somewhat of a JSON structure. So what this is giving, so you are sending messages. So this is chat mode. So messages is all the turns that you have had till now. So you can start the messages array. So this should be an array with all the turns that have happened till now. And the first entry can be a system prompt, right? So this is the extra thing that now we are adding. So earlier we were saying that the model was not properly following. So even though it was RLHF, it was not properly following the guidelines that we mentioned. So what you can do is you can give a system prompt and set some guidelines. Like say you are a helpful and knowledgeable assistant to an engineer. You can help engineers with complex questions. You can give anything like this. System prompt can be very long, and you can just list out in guidelines here. So you can say you should not be biased, you should not insult anybody, you should not say anything bad. Or you can set a rule, like say you are speaking to a children, you might be speaking to children, so you should make sure that you do not say anything that is not suitable for young kids, right? So you can set guidelines like that. So that is what goes in the system prompt. And how that gets converted to the actual prompt is this: so you have the starting token, then instruction, and this system tag that is there, this bracket sys, so this will contain the system prompt. And this comes before the actual conversation has even started, right? So this is the instruction, and beyond this all of these will be concatenated, like what is an atom and all these things, right? And then you can keep switching between roles. After that, the roles are user and assistant. So here I have just given one user utterance. So now notice one thing, that this did not work very well. So I asked about what is an atom, it generated something relevant, but it did not understand what this instruction was, these tags were. So this is happening because this client.chat API is coming from the GPT like family of models. So this was created by OpenAI. So that's why this tagging system is not working. So there are some chat models. So you can try using the Llama 2a7b chat. So that might work well. So I'm just hosting one model. So I was not able to change. But if you use the chat model, it will have some sense of these tags. So these are like some standard tags now that OpenAI uses. So some models are fine-tuned using them also. And if you find that these are still not working, you can fall back to this completion API, and there you can define your tags and like start working that way. Right? So you can define your system prompt before the conversation start. You can just simulate that. Okay, so that's the next example. Let me go. So as you can see, like it has generated a very long sequence and which has no value whatsoever, because this model was not like trained with that kind of those specific tags. Right. So what you can do is you can give this system prompt before your conversation starts, just like this. Let's say you are an AI teacher named Bob, you are giving a personality that you are helping a student, you should be fair, kind, etc. Right. Then you can have the actual conversation as new lines, and then you can just use the completion API to get raw model access. Right. And then it starts to generate something better, and it tries to uh, stick to that. Although it did not like follow this instruction that don't give student the answer directly, it did not understand that. It tried to give an answer. Right? But if you try the same thing with GPT 3.5, like the same prompt and the same guideline, don't give the answer directly, you can see that the model actually follows that. So this is a common challenge that we will face. So even aside from the knowledge problem, so I earlier mentioned that this large scale model will have large world knowledge, large access to world knowledge through their weights, large amount of like weights, parameter weights. These smaller models have lack of knowledge, and also they have like lack of knowledge, lack of understanding capabilities. So if the instruction or the text is too long, they cannot like make sense of all the instructions that are there, all the concepts that are there, right? So earlier Llama 2 failed with this instruction, so GPT 3.5 is able to do like fairly well, right? And also in GPT-3, if you are using GPT 3.5, it's easier for the model to like have consistent long-term conversations. With like Llama 2 or smaller models, it would become difficult. The initial few turns would be good, but after that, it would not be able to give very good responses. Right? So now all of these chat gpt models that you see, like so we have chat gpt, we have Claude, and these things, so they rely on very long system prompts, right? So system prompt is actually something very important to that. So this is just showing a snippet of it. So the system prompt can go to have like thousands of sentences, can be thousands of sentences long, right? So these prompts are frequently like curated by humans, where the models went wrong, where it was failing, and based on that they will try to correct and set certain guidelines, right? So these are changed day to day. And this common problem of where it is not following guidelines is also called jailbreaks. So what users try to do is they will go to say ChatGPT or Claude and try to get something which the model is not supposed to say, or something questionable, right? So that's what this game is about. So there are no great solutions to this, but this is the current way of doing things. So Yeah, so this was the first example. So if you have any questions, you can ask, I guess. You can pause for a moment. Okay, so if there are no questions, let's go ahead. Right. So what I showed is like still basic prompting. So you are just making your prompt richer, that so that in the guideline, so you try to build a guidelines over time. You give some more structure to the prompt so that the model does not fall off and generate too long sequences or go into repetition modes. Right. So all of these are good, but there are still unexpected behaviors that fails. So it can directly not follow the guidelines at certain times because these models are still limited in capabilities. So how well it can follow the previous context, and there can be loopholes also. So the users can find out, okay, this was the guideline, so what where might not have been mentioned in the guidelines, so we can just poke the model to generate something like that. So there is still some lack of controllability in this. So what you can do is, so you can continue to build. So what are the solutions is, you can continue to build complex system prompts. You can just continue to have like a team of people who will engineer these prompts to have better and better guidelines, find out where the models are failing and tag them, and add those examples maybe to the prompt also. So there can be other ways. So in certain scenarios, you can also do constraint decoding, like you know what the responses should look like, right? So for example, if you are in a banking system, so there you know the chatbot should only respond to certain things, and it does not have to go say do open domain conversation with users. So there, if you are using a LLM based system, you can have constraint decoding, that you say that if the question was this, there is this schema that the model needs to follow, and you make it follow that particular schema, right? And there can be ways of like more complex ways that you employ multiple LLMs as agents to kind of try to battle these sort of jailbreak attempts, right? So when say a user is trying to do a jailbreak with GPT-4 chat GPT, right? So there can be another LLM system, LLM like security guard sitting beside and looking at the chat that is going on, and it is working on a different prompt. So it will try to see whether the request that came in from the user has some malicious intent and or something, right? So there are these more complex ways of handling this. Right. Okay. So, and with system prompt also, like the same problems appear. You requires manual design, and the engineers that are there who are system developing this system prompts need to have experience with the system, like where it goes wrong. So that requires like, very good experience with what is defined as wrong or what the model should not say, and also when the model is going wrong, they should need to like go through the actual sessions of the user and try to figure out what are the problems. And with system prompts, the prompts can also get very lengthy, and this is one of the biggest challenges. So if the model has very lengthy prompts, it will take a lot of time and money to do these inferences. So if you go to ChatGPT or Bing Copilot, you will see that it runs a bit slower than just doing a normal API call. So when you are streaming, the tokens come much faster because there is a larger system prompt that is being deployed in these user-faced applications. Okay. So now let's get into a slightly more detail about how we can build such systems. So LLM agents is a possible way forward for building better dialogue systems. So LLM agents has the capability of handling complex tasks also. So now imagine that you have a chatbot, but you are trying to solve a task. So for example, if, say you are trying to tutor a student. So maybe tutoring a student is can be handled better by having rather than one teacher by multiple teachers, and each having a very specific role instead of having generic roles, right? And there the system prompt can be specific to that. So these are called agents. So when you have a LLM paired with a system prompt and a chat interface. So by chat interface, I mean like you have the agent and user tags going around. So just the LLM and system prompt may not be a chatbot. So all together we call these agents, and the communication mode is usually through a chat interface. So this is a singular like single agent, and the LLM agent systems usually have multiple agents built, like put together to handle complex tasks. So for example, you have a task which is to write code for students, like example code for students. So for example, if the problem was write a C code to print Fibonacci series, so you can just call the LLM with this instruction, that is fine. Or say the user asks you to send this particular utterance to the chatbot, it gives you a response. But that response may be incorrect, or maybe the task was so complex that the code is not solved in the first go. For example, you are trying to do a write a set of code. So there are two files, and you are trying to implement the actual Fibonacci series calculation in one of the classes in a separate file, and you want to have the main loop in the second file. So if you have tasks where this sort of complexities are involved, it might be hard to do in using just single LLM. So what you can do is you can build multiple agents. So that is just multiple system prompt paired with the same or different LLMs, and you can assign roles to them. And assigning roles is just you tell the system that in the system from that you are a system developer, you are a system designer, and then you like put down the rules, what it is, its most important task is, right? And so then what you can do is you can build systems like you have three agents, each of them, like the team planner can first get involved and figure out what are the steps, and the developer can just look at these individual steps one by one and try to write the code for them. So you can shorten the length of context as well using these approaches, so your individual calls are smaller. And since there is a quadratic increase when you increase the length, so splitting it to multiple calls would be cheaper also. And you can built in like have built-in tools also into this LLM agent, so you can call, have options to like call from the developer or the planner to call the compiler on the system to see whether the code is compilable. And if you're getting some error messages, you can again take that error message, put that back into the prompt, and prompt the developer, okay, this was the error message, what do you do, right? So all of these require multiple levels of automation, so that for example the developer can work with only like one kind of chat interface, but say the system designer is able to look at the compiler outputs also, and it can see that what is the task that the developer took, and figure out that the output that the compiler gave is an error, so it can decide what the prompt should be for the developer. So as you can see, like in multi-agent system, what you can do, you can also back and forth between these agents to build like a multi-agent dialog system to do prompting amongst themselves. So you just give the task prompt and your job stops there for now. And the agents will communicate among themselves through their prompting, like through prompts that they decide. They will prompt the other agents and try to figure out the solution. So there is a nice library called Autogen that tries to do this, and you can actually try using this. So this is the installation and the setup is pretty straightforward, but for the task you at hand, it may not work initially that well. So you just have to figure out like what the agents should be, how many agents you need to have, and what the prompt should be, right? So once you have that, you can try to do this. So yeah, so this is kind of like a meta prompting strategy. So instead of prompting the system and taking part yourself towards solving the problem, you are kind of meta prompting a system of multiple agents with the task instruction and let the systems prompt themselves, right? So this is a strategy also followed in chat optimization. Prompt optimization. So you can think of these agents being optimizers. So, or let's say one is optimizer, the other one is the actual model. So the optimizer can continuously call the developer, let's say that, okay, this prompt did not work, can you change the prompt, right? And then the planner can be the evaluator, so which goes through these examples and see, okay, what is my accuracy, right? So this has like this particular framework has a lot of potential in where you can apply it. Okay, so is there any question about this agents part?
Do we keep a record of all the interactions between the agents?
Okay, so you are talking about log of the previous interactions.
Yes, all the interactions, like you mentioned that one agent might give prompt to another.
Mhm. Right. Yeah, so those interactions are indeed kept in a log. So this is a structured JSON that usually is maintained at the backend. So first, whatever the user is giving, that is user's prompt or the task prompt. And beyond that, whatever the agents are saying to themselves, or like whatever the agents are writing as response or saying to other agents, are kept in that JSON, so that whenever required for the next step, suppose the agent 3 wants to see like whether the problem was solved, so it will query agent 2 and look at the responses from agent 2, like previous responses also, and based on that it will query agent 2, okay, what is the status of the current task. So this history is actually dynamically used by this system.
If the if there is any problem with the dialog system, then sometimes we would want to know which agent is actually not performing well or where the problem might be. So how do we track that?
Right. Yeah, that's actually a good question. So this is a common problem with any single LLM framework or even a multi-agent this kind of framework. So that's a bit difficult to do. So you can try to have constant encoding, sorry, constant decoding to prevent models from going haywire in their responses. For example, agent we can make sure that agent 3 is working with just smaller prompts or smaller contexts, right? So you can always summarize from agent 1 to agent 2 to agent 3, right? So usually these problems happens that you are mentioning are in longer prompts, right? So there what you can do, you can try to make sure that the individual prompts or context that they need to see is smaller, so you can have your own logic on top of this, so it's so that it's not just a simple agent multi-agent system, you are actually doing some supervision yourself also, right? But even after that those problems still might happen, and these are open questions. How do we make ensure that these systems do not go haywire? And coding tasks are actually one of the most challenging things. So in coding what has worked nicely is constant decoding and verifiers. So you can have a verifier like a compiler which looks at the output of the developer at every stage and gives it feedback, right? So while it tries to correct that code, and if you have constant decoding, you can make sure that the model is not generating something which is not a sensible code, and it follows the grammar. So there are different ways that are being explored currently to handle these problems.
Thank you.
Sir, I have a question.
Mhm.
Sir, can we use different LLM for different agent? Is
Yes,
it
definitely. Yeah, definitely.
so we can train LLM for different tasks and we can combine to solve the problem?
Yes, yes. Actually, that is a like good approach to doing this. So since GPT-4 it can be very costly if you have long tasks. Suppose you're trying to implement something, you can fine tune your own SLMs, or you can just have say a smaller SLM wherever it is possible to use that. So if agent 3 can be a smaller SLM, whereas agent 1 handles the most complex task, so that can be say 70 billion SLM. So you can have this kind of disparity between this based on your requirements.
Okay, sir. Thank you.
Okay. Anything else? So if not, let's move on. Okay. Okay. So the other problem that LLMs often face is LLMs can't remember previous conversation, right? So all of these approaches that we are seeing is that the LLM is tracking the current state of the conversation for the active interaction that is going on, right? So the state only holds that. But if suppose you have a chatbot and you have talked about something in the past, and tomorrow you come back and want to talk about like continue from there, or you want to consolidate two different conversations and have a conversation about all of these past conversations that you have had, right? So this becomes difficult with these current frameworks because LLMs cannot like remember the previous conversation, as you are throwing away the previous interaction history when you are starting a new session, right? And so this is problem one. The problem two is that this log of messages can get very long. So if you have, let's say, hundreds of conversations in the past, now in the new conversation, you are trying the LLM to remember something you had when you first interacted with the system, right? So you, the LLM has no way to access that specifically. Even if you say, like, you can say, okay, first remember the first conversation, but there is no mechanical or systematic way to access that from, like, infer that from there. So what you can do is you can store all of these histories and create a memory out of that, right? So this solves another problem, that these LLMs do not have access to new knowledge, right? So the, for example, GPT 3.5 cutoff was 2021, so that's like already 3 years now. So if you ask it anything about today's world, it will fail to answer. So how do you make sure that these models remain usable even after this, because you are spending so much in training these models? So you can create these models RAG first. So what RAG first means is you can train these models to be taking the approach of retrieval augmented generation. So till now, what you have seen is generation first approaches. So you are just giving a prompt and it is trying to generate something. So retrieval augmented generation is paradigm. What it does is you have multiple knowledge facts as part of your prompt also, right? So you give the instruction, there are multiple facts that can be present, more than one, and you ask the model some question based on that, right? So this is the, like, most promising approach right now to do it, to doing either question answering or remembering past conversations, or keeping the models updated with the new knowledge. So what these approaches do is you maintain a memory component. So this can be a database of facts or past conversations, and then you try to find out the best representative from this database for a particular context, right? So now if you have them in a database, how do you find out the most relevant uh, fact from there, right? So you can have hundreds of this, and since this is a free text, open-ended text database, you cannot really do a SQL query lookup, right? So you cannot formulate a query, okay, bring the fact which has answered to this question, right? So this is a complex thing. So what you can do is, and also the most efficient approach right now is called something called indexing. So in indexing approach, what you do is, or like modern indexing approaches, what you do is you take this database of texts and you encode each of them, right? So this encoding can be based on any encoder model or even like any SLMs. So you just pass this input text that is there in your individual facts, and you try to get an embedding out of these models. So for example, if you're using a BERT encoder, it can just be the CLS embedding. Or if you are using SLMs, so then you can think of like the last token embedding is a good candidate, because they are like non-autoregressive, or sorry, they're autoregressive, so they encode just in forward manner, right? So there you can use the last token embedding. And recently it has been shown that fine-tuned SLM can actually do really well in this. So you can, so there are some models like Grid LM and Clover Unity, which tries to do this. So they train these SLM models for this kind of tasks. And what you do is just that with the language generation loss, you add a selection loss also. So you have a selection task for given a query, you have to find out the most relevant document. You add this loss function to these SLM training losses. So they become very good for indexing purposes also, that you can use the last embedding, right? So when you have encoded all of your facts, so now from a database of text, you have a database of vectors. So from there, you can use various libraries like DiskNN, Fice, Scan, Pinecone to do fast lookup. So what these libraries do is they do approximate lookups, and it allows you to find the closest vector to your query vector. Okay, so there is one more step. So when you have a context for your conversation that is going next into the LLM, you need to find out the most relevant fact at this stage. So you encode that context, you get a vector, and that becomes the query for this indexing system. So you take that query and find out from the best or closest facts from this index, right? So, and whatever top key documents you find, you just add them to the context, right? So this is also called the retrieval augmented generation approach in general. And this actually can help you when using SLMs especially. So since SLMs can be fairly small, so they don't have much world knowledge, and they can easily start to fall apart in that they cannot look back in the past. right? So if you have a long context, it cannot look back. So you can compress your context in this way. You just take the whole context, put it in your database, and from that context, you pick the subset of it using such indexing strategies, right? And you just pass that context. So you can keep the context small, and this can help you build chatbots which do not generate responses which are not following the conversation. So you can prevent these kind of problems using this approach. Okay, so yeah, so this was the last topic, and if you have any questions for this, I can take. Yeah, I also have a small snippet for this thing. So this repo is by the available publicly, so you can just access this. I'll also share the link over mail. And yeah, so this particular code, so this is some other code. I'm just showing example usage of this files. So suppose you have a data set of dialogues, right? And the task here was that we have to find the most similar dialogues to a given context, right? So suppose you want the model to respond in a similar way. So this application was that given we have a set of dialogues in the data set which kind of shows you how to respond to certain context. So this can be useful when you have a very constrained environment where you do not want the model to respond in any open-ended way. You just always want it to follow the guidelines, and you have lots of example dialogues. So in this case, what you can do, you can encode your previous dialogues and pick out examples from that when a new query comes in, so that you look at the most similar dialogues in your context and do response generation based on that. So the dialog data is just a PyTorch dataset class. So what it is doing is like loading this text file and getting the individual dialogues, and then you extract out the context and the responses. Right. So remember that when a query comes in for the LLM, that will be the context for generating a response. Right. So that's why these responses are kept separate, and we are taking out the context, and this context would be the basis of our building the index for RAG. Right. So we take out the context. So this is just textual representation. So array of all the strings of context. And after that, let's say you have a model. So this can be a BERT encoder model or a SLM that gives you an embedding out of it. So you just take that and you encode all of these contexts, right? So you loop over this context. So train loader has the contexts, right? So you loop over these contexts, encode them using your model, and then put them in this array, right? So this array is now just a list of vectors, like 768 dimensional vectors. After that, using files is like just 2 or 3 commands. So first you initialize the index. So these are like some configuration that you have to give. So what is the dimension size and everything. So in this case, it was 1536 and dimensional vectors. And these are some specific things related to the indexing strategy that you are using. So these are first indexing methods. So what this does is like you can think of them as equivalent to you take dot product of the query vector with all the vectors that are there in the index, sort them, and just take the top k. So the libraries FICE has multiple methods for doing this in a more efficient way. So index flat, what it does is it takes the whole data set of vectors, it do k-means clustering over that, it finds centroids, and it just when you are giving a query, it first looks at the centroids only. So if say there are like 10 centroids, it will find out the closest centroid and then look inside that cluster. Right. So it's like if you have a hierarchical set of clusters, you can have log n, like your computational complexity would just be log n instead of a linear search. Right. So you once you have the index built, you do index.train over the list of embeddings that we had earlier from the context, and so this will give you the centroids. This will calculate the k-means cluster and the centroids. Then you add them. So this is just adding what are the elements. So these two steps can be separate, right? So you can train the index using say a much larger corpus, but you only want to search in a smaller list of vectors. So that's why these two steps are kept separate. Now, once you have that, you get a new query. So like this is the test time query. that comes in, you just encode the context, you search which is the closest index to that, what like the top k, this is top 50, what are the top 50 context to that. Then what you can do, so once you know which context are closest, you can retrieve what are the responses of those, and you can give those as example to the prompt, right? So this is how you can use the FICE index. Okay, so there are like a lot of libraries now which are focusing on doing this. So there are libraries like Pinecone also. So FICE is just for the indexing part, right? So this is like the raw library that allows you to build this fast search indices. What Pinecone allows you to do, Pinecone is built on top of such, so the disk library, which allows you to do not only search but also work with this OpenAI API. So it like sends the correct factual knowledge also database from the database to the prompt directly, right? So yeah, okay, that's all. So if you have any questions.
Yeah, sir. Hello.
Uh-huh.
I have a question.
Yes.
Code you just showed.
Okay.
And this index.train and index.add. Can you
Mm-hmm.
elaborate these two cells, what exactly they're doing?
Right. Okay. So what index.train and index.add is doing. So for example, your indexing and search strategy can be or like the indexing strategy and the index library can be different, right? So suppose you have a corpus. So what you might happen is, if you have, let's say, a web corpus which is just texts, so if you do index.train, what it can do is it can build a very granular representation of the different concepts because you are training it on a large corpus. But suppose for the actual task that you are trying to solve, it has a smaller example set for that. So suppose you just have hundreds of examples. So if you build a index based on only 100 examples, the index will not be that good. So what you can do, you can use a standard text corpus to build the index. So it will figure out what the centroids are for different concepts within the space of embeddings. And then you can add, so forget about that corpus now. Once you have found out the centroids, then you can just add this set of examples following that centroid. So it will just take these examples and put in them in the correct clusters, right? And so this is one usage. The other use case is, suppose you have built the context, built the clustering and built the index at some previous time point, and now you have got some more examples with you, right? So initially you did not have many examples, now you have got more examples. So instead of rebuilding the index, you can just add these new examples. So it will just find out the clusters for them and put them in the right cluster. So that's why these two steps are kept separate.
So let me reiterate what you said, whatever I
Mhm.
understand. So first in the above block of the quantizer files index, we are making the inverted file, or we are initializing the inverted file index,
Mhm.
and after
We'll
that,
initialize. This is just initialization. So here nothing is being trained.
okay,
Like we were just initializing, setting parameters and stuff.
after initializing inverted file, we are training on the text for centroids in the index.train, and then after that we are adding all the embeddings into the centroids.
Correct. Centroid clusters. Yeah, that is there. You are
Broadcast.
adding.
And sir, is it like you said, now it is not essential to retrain or recalculate the centroids? So,
Right.
but for the best case scenario, or we say to be on the safer side, we should
Correct.
retrain the centroids every time, I guess, before adding new vectors into it.
Right. So that's a good proposal, but you may not want to do it every so frequently. Like, so if you are getting, say, examples in a low rate, so suppose every day you get three quality examples, so there is no point in training this index again like every day just based on three examples. So what you can do is, but you still want to use these new examples that you are getting. So say for 10 days you just keep adding these examples, but after 10 days you will have 30 examples, or let's say every day is 30, so 300 examples after 10 days. So once you have many examples, it makes sense to change the index, like actually train the index again.
Okay, sir. Thank you. That makes sense.
Yeah. Okay, so I guess I will just cover the first slide and then okay. Right. Yeah. So like this is definitely better than in the past 20 years. What we have tried and all. So like we have made a significant leap in terms of what we can do in now like due to build dialogue systems, right? So a lot of new tasks are coming up and they are getting tackled by just using these LLMs, right? So the hope is high, but there is still some problems that the retrieval approach that I showed you, they are still suboptimal because they are using suboptimal models and old school strategies for this search. Right? We are still doing cosine similarity of these whole documents. Right? So that might not be the best way to compare your documents. So suppose you have a very long document and you have the answer hidden in one sentence somewhere in that long document, so it might be very difficult to get to that right document if the answer is just in a small portion. So the embedding may not be informative enough to say that the answer for every question that is relevant is there. Right? So retrieval is significantly suboptimal compared to the LLM reasoning capabilities that we have. So this is a very big open question: how do we train good retrieval models or retrieval that are at least as capable as the LLM reasoning? Right? So only if you have equal reasoning capabilities on the retrieval side, also you can expect to get good retrievals and get the correct answer based on the overall RAG pipeline. Right? The second problem is that the LLMs are extremely costly. So, for example, GPT-4, if you are prompting GPT-4, running this sort of academic experiments is out of question. So, if you just have a small data set of 100 prompts and or 100 examples, and you are doing prompt optimization, you can easily finish your GPT-4 quota of thousands of dollars within days, right? Because when you're running experiments and you are doing prompt optimization or some sort of training, you are actually making multiple prompt calls for each example, right? So this is very problematic. So then the question is how can we make SLMs as good as SLMs, as good as LLMs, so that we can actually use SLMs properly replace SLMs. So right now their replacements are in very specific areas. So for example, Mistral is very good at handling conversations. Llama 2 is good at getting it fine-tuned with some LoRa adapter, right? So they have specific use cases. So to make them as generic as LLMs is a big question. Then also, how do you train SLMs properly, right? So that is also a problem. So we don't know how to train them to as good as LLMs. So these are all research questions related to SLMs, and also if we can make LLMs on the other hand cheaper, that's also great. So the turbo models are in one way one solution to that. Like the actual GPT-4 is much costlier. The turbo models are almost 1/10 or 1/50th as costly. So that is some good direction there. So you can just distill these larger models to smaller SLMs, but that always does not work. And there are also approaches like these phi models. What they are doing, so instead of training SLM on a large noisy corpus, you can create synthetic data sets which are of high quality and just train SLMs on that. And you can focus on making them as knowledge rich as possible. So there are a lot of open questions in that area as well. And then the problem of how to optimize prompts automatically, right? So with these LLMs or SLMs, the only way of using them is giving them proper prompts to solve your problem. Now even with that, in many cases the LLM might just generate something that does not conform to your output data structure, so you would not be able to detect, or it might give wrong examples, and these models are very sensitive to the prompts that you are giving. Right. So with one prompt, your chatbot might be working well, and with some other prompt, might just be saying slangs to its users, right? So this brings in the question: how do we find the optimal prompt? And GPT-4 model, we don't have access to their logics even, and with SLMs we have access to logics, but prompt is coming from a discrete space, right? So even having logics, it's not very clear how you do gradient descent optimization on this. So this is open question. So many of the methods like Opro, Protege, what they are trying is they try to use a GPT-4 model itself as an optimizer. So that other model that I was explaining earlier in the LLM agents section, that other model works as an optimizer to optimize the prompt for this other model and sees what the performance that it got. So these are very ad hoc methods and they're not principled. And we often see that these approaches that are there, so they show good results on the task that they are optimized for, or like just on the data set. But as soon as you move towards a different task where the length of the context might be different, it might be different as the prompts again fail. So this is also a very challenging problem that we have no solution to. So yeah, so that is like the overall talk. So if you have any question from any point, we can go back and discuss.
I have a question.
Mhm.
Generally, there is some time for which there for retrieval. What would be a good when we are implementing such system? What would we consider a good retrieval time?
Okay, are you talking about the efficiency or of the retrieval?
Yes.
Okay, so yeah, so retrieval, the current approaches to retrieval are fairly efficient. So for example, the general methods that are used is either bi-encoder or cross-encoder based retrieval. So cross-encoder is difficult because what you do there is you take the query and you take every document, concat them, and try to use a BERT classifier or something to figure out whether they are similar or not. So although those give better results, they are very inefficient, right? Whereas the other approach is, and which we are able to make efficient using the libraries that I mentioned, like FICE and DiskNN, is that if you have a bi-encoded approach, so you encode the query and then you encode the document, like set of all documents individually, and then you see like what is the cosine similarity between them. So instead of tasking the model to find out the classification level, you are just taking the cosine similarity as your way to do classification. So this is extremely fast, right? So because as I told in the say the approach that I showed, so you can do clustering there using files. And if you do hierarchical clustering, what you can do is you have a tree structure. So you are just doing a log n time search over a size of n, like a database of size n, right? So the size can go up to millions, but your complexity would be still very low. So these files and all give very good ways to do this bi-encoder based retrieval, but they would not be very accurate because bi-encoder is just taking cosine similarity between the vectors. So one approach to make this more correct and also stick to the efficiency or the time constant is that you first do a bi-encoder retrieval or a file-based retrieval to find out the top, let's say 500 documents or top 100 documents, right, out of the million. Now, once you have the top 100 document, you take the cross-encoder model and pass all the 100 models with the 100 documents individually with the query to find a label for all of them. So this, since the cross-encoder model is more accurate, it is able to look at the document in more detail with respect to the query. It will give you a more accurate solution. So this is a trade-off you can do. So what is the value of your top k will decide how much time you're spending in the cross-encoder. And that is the majority of the time. So if you want to decrease time, you can just take top 10 and do cross-encoder on that, or you can take top 500, you can do cross-encoder that if you have more time. So yeah, does that answer your doubt?
Yes.
Right. I had a small doubt regarding the code itself. It seems I'm unable to understand like what does centroid denote over here, like the centroid IDs. Does it have to do anything with clustering? Are we like sort of
Yes, yes. So I was giving an example of doing this fast retrieval by clustering. So imagine that you have a million documents and you have a query. So to find the top 500 documents, you have to go through all the queries at least once, right? So that is the complexity of O of n, a linear complexity. And if you have million documents and calling the BERT encoder and the similarity function call would be very costly. Like it will take a lot of time. So what you can do is, so the basic idea intuition is that you take this set of million documents and just cluster them. right? So if you cluster them, you might get say 500 or 1,000 clusters. So instead of doing million queries, what you can do, if you just have a single level cluster, first you have to query the 1,000 centroids, right? And within each of these 1,000 you will have another 1,000 documents, so it's 1,000 plus 1,000, so 2,000 queries you have to do. Now, if you have a more complex clustering approach where you can go level by level, like first you have 10 centroids, then within each centroid you can have 10 more clusters. So then it will be even less complexity, right? So clustering is one approach to decreasing this document search or document retrieval complexity. So that's the example I gave. And this index inverse indexing thing actually does that. It does it based on centroiding, like k-means clustering. And there are other approaches also, other more efficient algorithms that are being used. So those are in essence doing some sort of clustering, but it may not be explicit clustering. It's just implicitly doing some sort of clustering.
Understood. Thank you. Hello.
Yeah.
So I had a question that if someone prompts this about something which is completely out of context, and using this method, no particular page is found containing that
Mhm.
particular context relevant to the query. So then,
Correct.
in that case, will there be any context retrieved at all or not?
Yes, that can happen. Yeah, that's a good point. It usually happens a lot, and I wouldn't say a lot, but it does happen some like often. And in that case, you will not have any context. That is true. And you can try something else. Like if you did not find it in your database, you can go fall back to a search query, like calling the Google or Bing API and getting some documents back from there.
Okay, thank you.
Yeah. Hello, sir.
Hmm.
So I had this question about indexing. Like we are using here inverted file, and there are
Right.
many other like hierarchical small word and Vamna. So I was particularly very much interested in Vamna, how it works, and how all its specialty that we can save it into the solid state drive, all our vectors, and we can do indexing inside the SSDs only. But
Hmm.
I was having a hard time replicating it, and so apart from that, I'm asking how much usability is that, because it seems like the rocks are in all this indexing methods.
Hmm.
How usefulness, there are are there some any disadvantage except that it is a bit unstable at times?
Okay. I mean, see, the indexing strategies that are there, like the clustering mechanisms and how the index is built, are agnostic to the task. Actually, think about if you think about it, right? So because all it is doing is based on some metric like cosine similarity or Euclidean distance, it will find you the closest matches, and that part is guaranteed. Like it does find the closest matches for some vector representation. So the question that comes in is how good your representations are, right? So usually that is where the fault is. So if you have a task which is you are not able to solve, like in case of say domain specific or the examples that you are giving, it might not be able to find the documents that rightly matches the database items, and that is probably because the representation that you have is not able to capture that feature. So one way might be to fine tune your BERT encoder that you're using for representation, or use a better, like more recent embedding model that is able to capture that feature. And oftentimes it is better to fine tuned models for getting this representation for specifically your data set.
Yes, sir. And I had one more question in the multi agent slide you showed, developer side. There were three agents. So
Right.
so I had this K. Yeah, can you show that slide?
Yeah.
Yeah.
Right.
So can we have this there like a fourth agent here where which will decide like which agent should be taken, like it should be a developer, system designer, or the expecting a query to be from of any type. So there is a developer, there is some agents of different, so we can make a routing some routing agent which will know where it should the query should be, which one of the LLM it should go to, so that it will
Correct.
save a lot of time and resources also.
Yeah, that is definitely true. You can actually do that, and usually there is some routing mechanism that are there in the AutoGen library, but it may not be that great. So you can actually explore that direction. So these are open spaces. So how to do the routing and how to decide which like the next step should be taken up by which agent and what should be the plan. So this planner that I mentioned, so the planner can be also something better. So the GPT-4 is not that great in planning, and so since GPT-4 is not good, SLMs are actually worse. So you can use say some external planner also to do this. So all of these are open questions, and you can actually think about that. So if having a fourth agent which routes these instructions properly, that definitely is useful, might be useful. Yes.
Okay, sir. Thank you. One last question.
Mhm.
Last question, not exactly related to what you said today, what you presented today, but I would like to
Mhm.
know what exactly are you working on in my MSR? Like, is it working on you are working on RAG or indexing, or just curious to know.
Okay. Yeah, like we have a few projects. So it's mostly, so we definitely focus a lot on retrieval. So our group is specifically focusing on retrieval. And by retrieval, I mean the retrieval side. So not RAG. So what the problem that I mentioned in the last slide, that retrieval is not of good quality. So retrieval is one problem that we work on. But we have some specific settings. So we may not be working on generic retrieval right now, but in certain settings, we're working on retrieval. And there are some prompt optimization problems also. So prompt is being used in many systems nowadays, like GitHub Copilot and Bing Search. All of these are now uses some sort of prompts for their interfaces. So there is a need for prompt optimization. So that is another one of the problems that I'm working
Thank you, sir.
Okay, any other questions? Question? Yeah.
Uh, Hi, so I just had another question out of pure curiosity. So, as you said that like normal retrieval processes, they have a linear time complexity which can get very tedious in the long run. So
exactly.
there was a effort to like bring in clustering to mitigate this time complexity issue. So
Right.
is there any other explored methods or any other theoretical methods that have been like devised that may serve better than clustering? I mean, as we see, like I'm actually mapping this to sort of unsupervised learning where like clustering was sort of revolutionary because it saved a lot of time and a lot of memory in that respect.
Mhm.
So they devise a lot of other unsupervised methods to, like build up on clustering and processes that are better than clustering. So is there any like similar sort of effort regarding RAGs?
Okay, so I'm guessing you are talking about the like the clustering part specifically, and or are you talking about retrieval as a whole, like retrieval for generation?
So basically, like you mentioned that clustering is being used to like improve retrieval time basically for
Mhm.
RAG models. So is there any other paradigm apart from clustering that has been explored?
I see. I see. Yes. So the domain that actually works on this is called fast search, or like So you are trying to find out the most similar search, right? So approximate nearest neighbors, right? So the clustering is just one approach here. So there are a lot of new papers that are still coming out. So this was fairly a old task, like when there was this big data and data mining was coming up. So this was a significant task that was used by the search engines at that point. Before it became of use for LLMs also, right? So there are a lot of research at that point, and the problem was generally of approximate nearest neighbor search, and that does not say anything about like what the approach has to be, right? So it just constrains that you somehow need to find out the nearest neighbors, and like it can be approximate. So since you are like doing like not going through the full list, so that's ideally what would happen. It would be approximate. So there can be some way which we have not discovered yet, which can find like the exact top k with some probability, right? So if you have top k, there is a guarantee that you will find k by 2 of them which are actually there. The top k by 2 is there. So that those are still question to be answered. But the main idea is that you find out some approximate nearest neighbors to that. This is the main overarching problem. And clustering is just one example that I gave. There are approaches like locality sensitive hashing, and DSKNN also developed something of their own. So all of these are there. So it's not just clustering that is the only approach.
Right. Thank you.
Sure. Any other remaining questions? If not, I hope this session was helpful for developing application using for dialog systems. And yeah, thanks Vishal for taking this up.
Yeah.
Yeah, thanks for your time.
Yeah, happy to be here. Yeah.
And I hope so. These things already shared. They will be shared with the participants.
Yes, I will share it on the same mail thread we were discussing. I guess you can follow because I don't have the email IDs for the participants.
Sure, and I hope you'll be fine if there are some question during the summer school.
Yeah, yeah, definitely, definitely. Yeah.
You can ask for email. Okay. So thanks, Vishal.
Yeah. Thanks everyone for attending. Yeah. Bye.